It's a true pleasure to be here. As Rajat mentioned, my name is Luca Carlone. I'm an associate professor in Aeronautics here at MIT. And today I want to tell you about the work we are doing on spatial AI for robots and autonomous vehicles. I will tell you in a bit what I mean by spatial AI, but the most important part here is to start by recognizing the students, postdocs, and collaborators who are doing the heavy lifting, behind the work I'm going to present. And Rajat should be here somewhere in the middle, so that's good. I didn't forget him. That's great. So a key motivation for the work in my group is to realize that there is still a large gap separating robot perception from human perception. For robot perception, we made incredible progress over the last few decades, and now we have very advanced mapping algorithms. For those of you who are familiar with the field, we have algorithms for simultaneous localization and mapping. We're at the point in which pretty much you can download from the web an open source library for simultaneous localization and mapping. You can wave the camera or move your robot around, and the robot in real time can build a 3D reconstruction, again in real time, of the environment the robot is moving in. That's kind of a purely geometric reconstruction. Let's see if I can make this work. Maybe not. Okay. So the one that you see in the video is purely a geometric reconstruction. It's just a collection of points representing the geometry of the environment. But this right now is commodity. We can just download and have this run in real time. At the same time, with the progress in AI and deep learning, we can now afford much better 2D semantic understanding. So for example, I can feed an image to a deep learning model, and the model can just group pixels into different semantic classes. For example, the colors here in the image at the bottom will define what is a car in blue, what is the ground, what are pedestrians, and so on. This is what is called a 2D pixel-wise semantic segmentation. So the great news is that progress in robotics, is allowing us to do both a very good level of 3D and geometric understanding, and also with the tools from deep learning, we can do some semantic understanding. But as humans, my point is that we are doing much more than that. Okay? And I will convince you about that just with a single image. So as a human, you can stare at this picture on the right for a few seconds, and just from a single picture, you can figure out what is the geometry of the scene. You can figure out that there is a road, there are buildings, there are cars, and so on. So you can picture what is the 3D shape of the scene you are looking at. You can understand the semantics, right? You can understand that there are people, there are cars, and maybe certain type of cars, which are the ones in yellow, are taxis. So you can understand a lot about the semantics. And you can even reason over relations between different entities in the scene. For example, you can think that a car is passing a green traffic light, or maybe a pedestrian is trying to cross the street. Okay? So this type of sophisticated reasoning over the geometry, semantics, and relations in 3D is something we are very good at as humans. It's something that we refer to as spatial perception. What we are trying to do is to replicate the same capabilities for our robots. And that gets to the concept of spatial AI. We want robots that are able to do the same type of spatial reasoning and spatial intelligence as we do as humans when we figure out from, for example, visual data, how the environment around us looks like. So the truth is that we are not just interested in designing better robots to match human performance. It's not just an intellectual investigation we are doing, but spatial AI is crucial for very practical things. First of all, spatial AI is crucial for interaction with humans. If my robot does not understand semantics, does not understand relations, I'm bound to give very low-level instructions to the robot. For example, if the robot just understands geometry, as in SLAM, I can tell robot, go to position X, Y, and Z. But personally, for the future of robotics, I would like to have a much more clever interaction with my robots, right? I would like to tell the robot, go grab me the cup of coffee on the table in the kitchen. And I would like the robot to have sophisticated understanding of the environment around it in order to parse and execute this complex instruction. So spatial AI is key to interaction. Some point that is a little bit more subtle is that spatial AI is also key to robust perception. And I really like this picture to illustrate this point about the connection between metric semantic understanding and robustness. So of course, as humans, if I show this picture, you see the car in the image, right? But if I show you the full picture I was cropping the car from, you can be a little bit confused for a few seconds, but then you can look at the picture and you can realize that actually the person and the car are not physically present in the scene. They are rather painted on top of the white van. Okay? So there is a white van with some sticker on top of it. And probably the reasoning that you did to get to that conclusion is that you looked at the ground floor, you realized that there is a ground plane, you detected the car, you detected the van, and then you realized that physically these two objects cannot be on top of each other. You reasoned over the relation between these two things and concluded that one has to be painted on top of the other. So the point I want to make here is that robust perception, as we do as humans, relies on simultaneously understanding geometry, semantics, physics, and relations in 3D. Perception is really about reasoning in 3D. Because without saying, if we pass the image, the very same image, to a state-of-the-art transformer model for semantic understanding, we'll not figure out the right content of the scene, and we'll understand that there is a physical person there, we'll understand that there is a physical car there, we'll not be able to do the complex reasoning that we do as humans. So a lot of the work in my lab has really gone into trying to figure out how we can enable this type of geometric, semantic reasoning for our robots. And we started several years ago, I think this is probably 2019, developing Kimera, which is a library for real-time metric semantic localization and mapping. So what Kimera does, at least on the surface, is pretty simple. Kimera will take images from camera, so you see the images at the bottom over there, and we reconstruct from this input a 3D reconstruction of the scene. We reconstruct a 3D model, 3D mesh model of the scene. So what you see here is not just a video, it's just a 3D reconstruction of the scene, a 3D mesh of the scene. But not only we reconstruct the geometry of the scene, we'll also attach different semantic labels to the mesh. So what you see is that the mesh is color-coded. Actually, the labels that you see in the mesh are not real colors. They correspond to different types of objects. So for example, gray will be the ground, green will be the walls, light green will be the chairs, yellow will be the cubicles, and so on. So the robot with this kind of, with Kimera is able to understand both the geometry and the semantics in real time and in 3D. Equipped with this understanding, you can imagine now we can have our robots, for example, execute complex instructions such as robot go grab me the cup of coffee. And a lot of the work we do, we're very proud of that, is released open source. So you can download Kimera and run it in real time on your computer. There are, of course, many technical details. I will not go through that in the talk. But essentially, behind Kimera, we are solving a lot of geometric reasoning problems as well as optimization problems. And I will talk a little bit about those in the second part of the presentation. After reconstructing this type of 3D metric semantic maps, we quickly realized that that's not enough to execute complex instructions from humans. So take, for example, an instruction such as robot, go search for survivors near the fridge in the kitchen. We realized that this instruction includes concepts such as kitchen, which is not really an object, it's a room, it's some more complex concept. So the point here is that in order to execute complex instructions, robots need to understand semantics beyond objects. So we need to understand rooms, buildings, humans, and so on. Moreover, they need to reason over relation between elements in the scene. If you look back at the instruction I provide, the instruction says, go search for survivors near the fridge in the kitchen. So near the fridge and in the kitchen are type of relations that the robot has to understand in order to execute this properly. So therefore, we came up with a new representation, a new mental model that the robots can use to represent 3D environments, which is what is called a 3D scene graph. So we'll animate this video and walk you through this representation. A 3D scene graph is a hierarchical representation in which at the bottom layer, you have a 3D metric semantic mesh. That's pretty much the same as in the previous slide. But as you go up in the hierarchy, you are abstracting away dense geometry into semantic concepts. For example, objects, rooms, buildings, which is pretty intuitive as humans. It's pretty much the way you think about buildings or indoor environments in general. And there are other layers here which are a little bit harder to understand for humans, like places and structures. Structures are pretty much walls, ground, and so on, and places are a representation of the free space the robot can navigate in. So we proposed this representation. We also proved quite fundamental results about this representation, saying that if you arrange things hierarchically, you get to graphical models which are much nicer for inference. Actually, full credit for this is to Rajat, who is the mastermind behind this result. So what we proved is that if you arrange things hierarchically as a graph, the corresponding graph-based representation has small tree width. For those of you familiar with graph theory, you know that the tree width is a measure of complexity of a graph. If you can prove that your graph has small tree width, it means that you can do efficient inference, you can do efficient algorithms over this representation. So it's clever to model things hierarchically. Of course, we didn't just stop at proposing a representation and proving some fundamental property around it. We also developed the first algorithms that can build in real time these kind of 3D scene graphs as the robot is exploring an environment. So here, just to lay the setup, you will see the image collected by the robot as it goes on the top left, and you will see the scene graph getting populated in the middle of the slide. So in this case, you switch on the robot has no idea about the environment. It's starting in a kitchen, but it doesn't know it. And as it goes, it's able to estimate its own trajectory, which you see as a yellow, greenish line, here in the plot. It's able to understand and localize the presence of objects, for example, that there is a sink, fridge, appliances, and so on. And from this collection of objects, it's able to figure out that the room it started from is a kitchen rather than a bedroom. So you see that it's able to create this hierarchical graph in which there is the mesh at the bottom. There are a collection of objects, which are these boxes in the middle. And there are notions of rooms at the very top. Okay? So to get this, you have to fuse essentially traditional work on simultaneous localization and mapping, which is about reconstructing the geometry of this environment with novel tools from deep learning, and in particular, graph neural networks. And indeed, what we do is to come up with new architecture for graph neural networks, which are called neural trees. Again, full credit to Rajat for this, which are essentially the workhorse behind taking the objects and inferring what is the type of room the objects are in. The resulting system is something that we call Hydra. Again, we do a very good implementation of these. You can find a C++ implementation online and just run this on your robot. And of course, the same idea about organizing map representations hierarchically is very intuitive for indoor environments. You would have rooms, buildings, and so on, but you can apply the very same idea to outdoor environments. Maybe you want to group trees into a forest, or you want to group roads into a neighborhood and then a city. You can still have some hierarchical organization, even in complex outdoor environments. The catch in outdoor environments is that you do not have a lot of training data. Turns out that if you want to have training data to build these scene graphs for indoor apartments, you have standard data sets to do that. For outdoor environments, you do not have the same availability of data. So actually, we use large language models to have some prior understanding of priors, essentially, on where certain objects are found. For example, a bunch of trees can be found in a forest. So we interpret and we use the results from large language models to understand these priors. And we enforce these priors doing the 3D reconstruction using a tool which is called logic tensor networks. And the result, again, is that the robot is able to move around. This is a ground robot. He's driving around. He's building this 3D reconstruction. He's attaching different colors corresponding to different pieces of the reconstruction. There can be chairs. There can be trees, and so on. And again, there will be some neural network which is taking the objects and inferring that the robot is partially moving, is definitely moving outdoors. And in a second, we'll show that, let's see if we get there. We'll show that there is a walkway, there is off-road, and so on. So we'll cluster essentially the environment into different regions. So what now? We're able to build nice hierarchical representations of the environment. What can we do with that? Turns out we can do a lot. And we've been showing that if you have a hierarchical representation of the environment, you can do much more efficient path planning. You can do hierarchical path planning and just speed up the process of path planning by orders of magnitude. We show that you can actually feed this representation to reinforcement learning and do much better, for example, object search or different tasks which are RL-based. And also we show that these representations are quite efficient if you want to start sharing them across multiple robots. So the ones at the top are essentially our works. The thing that is even nicer is that a bunch of other groups are starting to build on this 3D scene graphs idea, and essentially are showing that you can use scene graph for task planning, for goal navigation, and for other robotics applications. OK, I will switch gear now, and I will look back again at the gap between human and robot perception. As I mentioned at the beginning, this gap is in terms of the richness of the model we form as humans, but is also in terms of robustness. So in the rest of this presentation, I want to zoom in a little bit more on the topic of robustness and tell you about the work we have done to improve robustness of perception algorithms. It's going to get a little bit more technical, which I hope some of you will enjoy. So it turns out that behind the nice videos I was showing in the first part of this presentation, there is a lot of math. There are a lot of optimization problems, and in particular estimation problems that you are solving. in particular when it comes to object pose estimation from 3D data, such as point clouds, or object pose estimation from images, or even like, the topic of simultaneous localization and mapping. In the back end of these problems, you are solving an optimization problem. And the optimization problem takes like, quite simple form, which is the one I'm showing here on the slide. In this optimization problem, you're trying to figure out a variable x. For example, if you're trying to localize the object, the x will be the position and orientation of the object in 3D. You're given a number of measurements yi. This can be, for example, detections of points which are on the objects, which are these green dots or yellow dots in the image over there. And you're figuring out the x by minimizing a residual error r, which is measuring how well a given x is fitting measurements yi. And of course, you have a bunch of measurements, a set of measurements, capital M, okay? So if you look from outside, this problem looks pretty easy. It's a least squares problem. The main issue in robotics is that the measurements are not great. They are definitely noisy, but some of them are outliers. So some of them can be completely wrong. For example, if you have to detect what is the position of the car here, you want to use these features. And these features are typically extracted by a neural network. So some of them will be good, such as the ones in yellow here, but some of them will be completely incorrect, like the one in red. And the same problem shows up like in SLAM. Some of the measurements will be completely off. So you want to figure out the x, the variable you care about, while discarding the measurements which are not great. So for those of you familiar with estimation, you will say, Luca, well, people in robust statistics figured this out like in the 80s or maybe in the 60s. We just have to put a robust loss function in the optimization problem, and we are robust to outliers. Well, the thing that people in robust statistics didn't really tell us is how to solve the optimization problem. And indeed, you can prove that this optimization problem is probably hard. It's probably inapproximable to solve in polynomial time. That's the reason why people in robotics have mostly used local approaches. Think about gradient descent, or things like Ransack, which is a sampling-based approach. It's very easy to make these approaches fail. But the thing that really bothered us when we looked in this line of work is that these approaches essentially fail without notice. We'll tell you, this is a solution for x. The solution can be completely wrong. And these algorithms will not be able to tell you that they give you a wrong solution. Okay? So we said, can we do better? And that's what led to us proposing this idea of certifiable algorithms. A certifiable algorithm is an algorithm that computes an estimate for this optimization problem I was talking about, and either certifies it is the optimal estimate or will declare failure. You declare you will not be able to trust the estimate instead. Okay? I wish I could tell you about a single algorithm, but the truth is that we developed really a toolbox of methods in this, on this topic, ranging from graph theoretic techniques for filtering out outliers, to better techniques for optimization based on what is called graduated non-convexity, to moment relaxations, which are really the key idea if you want to certify optimality for an estimate. And I'm out of time, but I will still try it. I want to give you one slide overview of what is the idea behind these certifiable methods. I'm from Leeds, so I feel that I need to have a slide with a little bit more mathematical underpinning here. If you don't follow these, don't worry, but it's cool math. So at the end of the day, we want to solve an optimization problem, which is the one at the top. This is about robust estimation. We want to figure out the x by solving this optimization problem. Well, what we do is to come up with a fundamental insight, which is for the problems we care about, you can take the problem at the top and manipulate it into what is called a polynomial optimization problem. That sounds scary, but it's something very simple. A polynomial optimization problem is an optimization problem in which both the objective and the constraints are just polynomials. X1 squared plus 2x2, usual polynomials. And the nice thing is that after you get to a polynomial optimization problem, there is a pretty simple way to relax that in a convex problem, where convex means essentially easy to solve problem. Okay? So you can transform the original problem into something that is convex, something that is called a semi-definite relaxation. And the last problem is actually pretty easy to solve. So what we did is to come up with better solvers to solve the convex semi-definite problem at the bottom. And we also propose this idea of estimation contracts in which after you solve the problem, you get some guarantees about how far is the solution from the ground truth, from the actual location of the car that you want to estimate. Okay, so let me close the math here. We have been instantiating this idea of certifiable algorithms in many, many applications. So we have algorithms which are able to estimate the pose of objects from point clouds, estimate the pose of objects, as well as the shape from point clouds, or do localization and mapping. Everything is released open source, and we get a performance in which these algorithms are able to tolerate a large, extreme amount of outliers. And some of these have been quite successful in practice. Some of them are even included in MATLAB at this point as standard algorithms for localization and mapping, for instance. We had fun for our projects in applying this idea of certifiable algorithms across many application domains. We participated with JPL in the DARPA Subterranean Challenge, where the goal was to deploy robots for doing large-scale mapping of underground environments for search and rescue. We won first and second place in 2 out of the 3 competition. We've been working with Ford and NVIDIA to deploy these to make self-driving cars safer. And one of my favorite applications has been to use this technology for terrain relative navigation, which is pretty much like pose estimation from images applied to aerospace applications. And my students were fortunate enough actually to fly their algorithms on literally this rocket, which is the Blue Origin New Shepard rocket, flying, I think, a couple of years ago at this point, and testing their algorithms on these platforms. So I could show more about this application, but actually I want to conclude just by showing an application that I find really cool, which is about using these algorithms for certifiable perception and pose estimation to the problem of aerial grasping. Okay? So we said we want to design a drone which is able to identify and localize objects of interest and quickly grasp them. So we came up with this concept. Actually, that's a photorealistic simulation. It's not really a concept. A few years ago, in which we designed this new platform, we put a soft robot as a gripper on top of the robot. And essentially, we enabled this platform to both detect objects and grasp them real quick. It took a few years, but actually we have now real prototypes doing pretty much the same job on physical platforms. So what you see here is a robot which purely using onboard vision, onboard cameras, is estimating its own location, and is also estimating the location of external objects, and is planning a trajectory to aggressively grasp an object, in this case, at up to 2 meters per second. So in conclusion, today I described some of the work from the lab on spatial AI, talking about robustness, talking about human-level type of understanding. And of course, there is a long way to go to match human performance. But to conclude, what I want to stress is that the payoff is huge. If we can get spatial AI capabilities, essentially we can design the next generation of robots that can power search and rescue for disaster response type of missions, can power precision agriculture to improve food production, and really create a better future, can power planetary exploration and form, for example, the vision-based navigation system that will take us back to the moon, as well as just make our self-driving cars much safer on our roads. So if you're curious about this work and you want to learn more, you can visit our lab. The lab is called the Spark Lab, or you can reach out. And of course, I will be happy to take questions, and I will thank you for your attention.
So we have time for questions. Yeah, you can use.
Yeah, can you hear me?
Yes.
Thank you. The talk was really cool. So given the time you spent talking about how robust the Kimera approach is and the Hydra approach is there an equivalent to having the van with the Porsche painted on the side for the 3D case? Is it a toy car that it thinks is a real car, or is it just robust to the point where that doesn't happen?
Yeah, I mean, the point of that picture is that that ambiguity is mostly in 2D, but if you start reasoning in 3D, essentially that ambiguity goes away. So I don't know if you can come up with kind of hallucinations or similar things in 3D, but the point is that with Kimera or with Hydra, a lot of these corner cases will go away, just because you're able to reason in 3D and figure out that 2 things cannot be on top of each other. That's my take.
Cool, thanks.
Thank you.
Any more questions?
I was wondering, in these hierarchical representations that you showed for Hydra, how abstract or how can it work with abstraction? So, for example, I'm thinking of a problem where maybe it can plan a trajectory using high-level abstractions of just room to room, but you have to consider that one of the rooms, for example, is a very tight space and difficult to navigate through, and so your trajectory will actually also be affected by the low-level information that you're using. And how do you sort of seamlessly go through low-level and high-level information when making plans?
Yeah, it's a great question, actually. Like, you know, I can tell you what we did and what we are doing. So in what we did, which are the results I mentioned on hierarchical planning, we are very naive about that. So essentially, if you have to plan hierarchically, we are planning across a very large scale environment in multiple buildings. So we first start, like, you know, planning at the level of buildings. So to reach the goal, you have to go through building 1, 2, and 3. Then for these buildings, we plan at the level of rooms, and we get a sequence of rooms. And then, like, you know, limiting to this set of rooms, we plan at the level of places which are more of a fine-grained representation of traversability. So naively, we go down, assuming that we'll be able to refine the plan going down. So that's, like, you know, the naive way. The pitfall is that maybe, like, you know, when going down, you can figure out that actually you cannot traverse a given room. The proper way that we're trying to explore right now in a collaboration with Nick Roy is something that you heard from Leslie, which is thinking about task and motion planning, thinking about, you know, problems in which you do have, like, you know, this kind of two levels, one which is more symbolic and one which is more, like, you know, geometric, and you want to go back and forth within the two to find feasible plans. So we're working on that, and it's definitely a great question about if you have multiple levels of hierarchy, you take advantage of that. It's something I'm insisting a lot with my students about. We do not have a great question yet, but the intuition is that the hierarchy should buy you a speed up somewhere.